Hey, what's going on YouTube? I think that we're live. Welcome back. So this is another episode today, learning proofs, learning proofwriting strategies. We are in the middle of building the number system. So literally just regular numbers, a plus b equals b plus a raised to the b, 0 raised to the 1, 0 raised to the 0. We've done, if A, then B. So we are learning proofwriting. And in particular, we're learning proofwriting in a very modern way using Lean. Lean is a new proof-assisted mathematics system that basically can translate mathematics so that a computer can understand it. And it's all built on type theory, which is a beautiful field of math/computer science. And it's really close to the type of work that I've done as an iOS developer for the last 10 years. I love static type systems, and so the fact that math is going this direction into reformulating and replacing set theory with type theory is a very, very cool thing to me. So, where are we? Today's like the third or fourth day. I guess it's the fourth day this week, learning Lean. Yesterday we got through, I think, all of multiplication world. I think yesterday we did implication world. So we learned how to write down statements like if A, then B, and how to use that in another proof. So in another proof, if it's true that you have A, then you can use the prior theorem that you have, if A, then B, so that in your new proof, you know that B is true. So by A and B, right now, I mean sentences like 2 plus 2 equals 5. That is a false sentence. So these are called statements, propositional statements. They have a truth value of either true or false. So we did implication world, and we did about half of power world. So in power world, we're continuing the binary operations on numbers. So we started defining things like 0 raised to the 1, or 2 squared equals 4. We're doing literally proving things, using proofs and rigorous mathematics to prove that 2 squared equals 4 and 2 cubed equals 8, for example. And we prove all this from very simple assumptions called the piano axioms. And so all of this math that we're doing this week is classical in the sense that you can write out all of these proofs on paper. I took a course in college, and it was part of our intro to proofs course where we saw how you build arithmetic using the piano axioms just on paper. And so this week is literally intro to proofs, intro to classical proofs, but it is also intro to Lean and modern proofs. Where are we? We're playing the natural number game, which is a fantastic, wonderful tutorial for learning Lean. It is very video game themed, and so I hope you play along with me. Pause the video at any time and try to solve these exercises for yourself. There's a terrific website, so you don't have to install anything to your computer or anything boring like that. As a software engineer, I know that often installing software is like the most annoying and error-prone and difficult thing. Just installing Ruby on Rails, and how every single time something like Puma is missing libSSL, and why is it missing libSSL why haven't we figured this out yet? Things like installation is and configuration of your system is one of the most annoying things. And so I can only imagine how annoying it would be to pure mathematicians who have not been living with Git and version control and pulling and pushing to GitHub and all of this technical stuff that's annoying for software engineers. I can only imagine how annoying it is for people who are used to doing math on with a quill pen next to an oil lamp. Like if you're used to that and now all of a sudden you have to deal with compile times and continuous integration, CI/CD, thinking about regressions, and like unit testing. Does MathLib have unit testing? Is that a thing? It should. Like I bet it does, but yeah. There's a whole world of software engineering that it seems like math is now coming into, and like we're taking the world of software engineering and applying it to pure mathematics, which is not something I ever expected would be a thing in my lifetime. But now that it is happening, and it's pretty new still, like over the last, 6-8 years or something. In the world of mathematics, 8 years is like a blip. Like usually in undergrad, you don't learn anything past like 1900 or something. In undergrad, you don't, like, all the math that you see is at least 100 years old in undergrad. And so it's very cool that we can be doing undergrad intro to proof, intro to math, intro to real math, with some math that's only 8 years old, or 10 years old. I don't know exactly, less than 10 years old, let's say. So I think that's freaking cool. Let's continue. I'll stop yapping. I hope that was an interesting introduction, interesting enough. And yeah, I will briefly say that on my other channel, I just uploaded a short, and I was excited to upload it, and it ended up taking like 45 minutes, all things considered. And I wrote down my thought process with timestamps of every single little product point, every single little point of product friction. And I have like 30 criticisms of YouTube that I wrote down in the process. And it ended up taking like 45 minutes just to upload a 1-minute clip, let alone the time it took to make the clip before trying to upload it. So that's absurd. That's just absurd. This channel and everything I'm doing is meant to be deliberate practice. I'm not just practicing math and practicing technical skills. I'm also trying to practice product skills. I think if I go back to a tech job, if I end up moving back to Silicon Valley and working in tech again, I think I'd like to be a product manager. How dope would it be if MathLib needed product managers? If like math engineering became a thing and we needed product managers to like lead projects in math engineering, like that would be freaking cool. I would love to do that. So hit me up, Kevin Buzzard, if you're watching this video. I would love to help you formalize FLT. Like, very much. I'd be so motivated. I'd almost volunteer to do that. I wouldn't volunteer to do that, but almost. All right, so where are we? Why is OBS not working? Software just... You look away for a second, and then software just doesn't work. Why? Okay. Restart capture? Okay, why do I have to restart capture again? It doesn't normally do that. Okay. All right. Now we're ready to go. Let's do this. Let's keep playing this brilliant, fun video game. I am not an expert leaner, y'all. I'm learning. I'm literally learning. What did we do yesterday? So yesterday we have been working through as I said, we did implication world. How do I get to the map? Is there a quicker, oh wait, okay, home. Click on this first bubble. Here we go. Okay, so let's review what we did yesterday. We did implication world. I guess I'll just show you the titles of everything. So in implication world, we learned the exact tactic. Oh, dang it, I need to switch here. So in implication world, we learned the exact tactic. Then we practiced exact. Then we learned apply. Then we learned that the successor function is injective. We learned how to argue backwards. We got an intro to something, lowercase, intro, what? All right. I might open a pull request for that one if I get around to it. Oh, intro, the tactic, intro. Were the prior ones backticked? And that one wasn't? No, I think all of these could use backticks. Oh, yeah, no, I thought so. Some of them are backticked. Like apply is backticked, which told me visually that it's a keyword. Here, I think suck-ing should be backticked, and intro should definitely be backticked here, because that threw me for a loop. I was like, intro? We did an intro in section 1. All right, and then intro practice. So intro, go watch my other video if you want to learn what that is. Then we've got the not equal sign. So this is an implication. It's truly an implication in disguise. Then we learned 0 not equal successor. So 0 doesn't equal anything plus 1 is how I would phrase it. 0 does not equal any natural number plus 1. 0 is -1 plus 1, but right now we're not working with negative numbers. Negative numbers are not natural. Negative numbers are imaginary. We created them. We invented them. In the real world, what we can see is a positive number of objects, of acorns or coffee mugs. So all the math that we're doing right now is natural numbers. Then we learned that 1 is not equal to 0, and then we proved that 2 plus 2 is not equal to 5, and then that was it. That was the big boss. That was our goal of implication world. Literally, I spent like an hour proving that 2 plus 2 does not equal 5, and I had so much fun doing it, and you will too. All right, so now we're in Power World. We got an introduction without backticks. We've got 0, pow 0. And here, this is a little controversial. In lean, we want everything raised to the 0 to have a single value. And so in lean, we say that 0 raised to the 0 is 1. That's a little controversial, because in calculus, you'll learn something called L'Hopital's rule, that sometimes it's 1, sometimes it's 0. But in lean, we define it and we just make a decision and say, let's just pretend it's always 0. Or wait, is it 0 or 1? Well, yeah. 0 raised to the 0 is 1. Little surprising to me, but yeah. So now we've got this theorem, 0 pow successor. For all numbers, 0 raised to a positive integer equals 0. And this is something we can prove. 0 raised to I read successor m to mean a positive integer. So it's not 0 because it's something plus 1. Successor is like plus 1. So 0 raised to a positive integer is always 0. And we don't have to assume that. We can prove it. Then we did any number raised to 1. We proved that anything raised to the first power equals itself. A raised to 1 equals A. Then we proved 1 raised to anything equals 1, which is slightly different. Then anything squared equals it times itself. So this is cool because at least in grade school, you say that this is what this symbol means. Like you take exponents as, like the definition of an exponent is that it is a times itself with two terms. But in lean, and I suppose also in piano arithmetic and in the piano axiom system, this is actually a theorem. It is something that you can prove, not have to assume. You don't have to assume it. Then we've got pow-add, which means we proved this fact that we all learned in grade school, that when the power is an addition, m plus n, then this splits as a to the m times a to the n. That's pretty cool. So these are things that we're proving. Now we've got multiplication raised to a power. So the naming convention is very important. The order of these function names or of these theorems is important. First we have a multiplication, then we have a power. So AB quantity raised to the n is a to the n times b to the n. We proved that. Then we've got pow-pow, which just looking at that makes me smile because it sounds nice. Pow-pow. But it's meaningful. So I'm expecting to see one power and then another power. So I can guess that means a raised to the b raised to the c equals a to the bc. Or in this case, we're using m and n. Yeah, a raised to m, quantity raised to n is the multiplication of those powers. So it's cool to see that the naming convention describes the left-hand side of this rewriting rule. It describes the left-hand side. It doesn't say pow-pow equals pow-mol or something like that. I don't know if that's always the case. I think so. Pow-pow says a power raised to a power, and then the right-hand side is as you expect. All right, and that's how far we've gotten. So I haven't actually proved this one yet. We will start this one. Looks like something went wrong. I'm going to ignore that. So my goal is to prove a raised to m raised to n equals a raised to the m times n. This is our goal. Before we get started, I'm going to check chat. Nobody's there yet. Well, somebody popped by. They hit the like button. Thank you for hitting the like button. If you see this right now, hit the like button, please. It helps so much, especially as a brand new channel. It helps a brand new channel get off the ground really well. So if you're still watching this, you must be a fellow nerd. Hit the like button. We're already like 20 minutes in, and all I've done is just review what we did yesterday. So sorry, I yap a lot, but the beginning of these videos should be review and kind of quickly showing what I did over like 2 or 3 hours yesterday. So I think everything's working as expected. We're going to prove this power rule. How does this stuff work? So I'm still new to this. Let's see if I can remember. What do we do here? All right, so we're going to do some rewriting rules. What I think we're going to do is an induction on the second power. Yeah, I think that's what I want to do. So I'm going to write the human readable proof, partly for myself, but then partly to show you all what a classical human readable, if you write it on paper next to your oil lamp, what should it look like roughly. the proof will be by induction on n. Maybe I'll write it in full English sentences, like it would be a real proof. We'll prove this by induction on n. A lot of people don't see pure mathematics. You'll all only learn basic engineering mathematics. In pure mathematics, you write full sentences. And you try to avoid fancy symbols, even. You write out a full sentence when you can. It's important. We'll prove this by induction on n. First, we show the base case. The base case, let A and M be natural numbers. Some authors will type out those words, and then others will do a fancy symbol. This E means that it's an element of the second symbol. Those two sentences mean the same. I'm okay with element and blackboard N. I'm okay with that, personally. Let A and M be natural numbers. Well, I guess all of them. Let A, M, and N be natural numbers. Oh, wait, no. I knew what I was doing. Then we want to show A raised to the M raised to the 0 equals A raised to the M times 0. So I'm going to at least line split this per sentence, but in Intro to Proofs courses, you would write this as a paragraph. Just write it like a regular paragraph. To do paragraph breaks, I'll put like an extra line in between these comment sections. So it's okay to do something like centering, and say A raised to the M raised to the 0. I think that we have anything raised to the 0. Do we already have... Okay. Yeah, we're proving power rule. A raised to the M raised to the 0 equals 1 by definition of raising to the 0. Again, we have the slight problem of if the base is 0, but so I'll just put it in parentheses. The definition of anything raised to the 0 is 1. We also have, let's say that this would not be centered. We also have the right-hand side, A raised to M times 0 equals A raised to the 0. So you don't need to write every single little detail, like by multiplication of 0, M times 0 equals 0. In math, you can be a little informal depending on your level of math. And depending on the class, but usually this would be okay. And then thus the identity holds, or the equation holds, and the base case is done. in induction, we always prove something for the base case of the number equals 0 or the number equals 4 or whatever, and then we show that for every number after it, like 0 implies 1, 1 implies 2, 2 implies 3, etc. Next, we prove the inductive step. Next, we prove the inductive step. Assume that a raised to the m raised to the n equals a raised to the m times n. We want to show that then a raised to the m raised to the n plus 1 equals a raised to the m times n plus 1. I'll keep the parentheses there to be like extremely explicit. And in math proofs you can usually use little shorthand like want to show. WTS is very common, with or without the with the dots. We want to show that blah 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 equals blah blah blah. And it depends on if you're writing a paper versus completing a homework set. But anyways, so a to the m raised to the n plus 1. Let's see. By definition of x raised to the n plus 1. So in piano arithmetic, we define raising a number to 0, and we define raising a number to n plus 1. So the next version, or yeah, the next number after n. Hope that makes sense. Times a raised to 1, which is just the same as, times a to the m. So, yeah, like if you raise a number x to, let's give a concrete example. X cubed equals x squared times x, right? X to the 10 equals x to the 9 times x, on and on. That's what this is showing. Then a to the m raised to the n times a to the m equals, so I'll say then by the inductive hypothesis, maybe we'll center these in our homework so that it looks nice. A raised to the m raised to the n times a to the m. The inductive hypothesis, we assumed that a raised to the m raised to the n equals this. I'm sorry that the contrast doesn't look great, but we're on line 12. Is that an inductive hypothesis? So we've got a raised, we can substitute that part, and then we have a raised to the m. By definition of again, by the definition of raising something to the next number, let's take all this. a raised to the m times n times a to the m equals, oh wait, we have to modify this ever so slightly. We can't do this one just yet. By, oh wait. Where are we? It would be easier for me to see this stuff if I wasn't using ASCII, but drawing with positional notation. Assume a to the m. We want to show that this left-hand side on line 13 equals this right-hand side. So we got that part. A raised to the m times n. I'm going to clean up just a tiny bit and get rid of these multiplications where I feel that they're not necessary, like mn. A raised to mn times a to the m. Because I keep feeling like we already... Shoot! A raised to the mn times a to the m. Keep wanting to go one backward to something that we already had. A raised to the mn. So we came from here. Probably doing like a long chain of equalities in the center of the page would make this easier than breaking it into separate sentences each time. But yeah, like, feel pretty good that this is the first step. The definition of power raised to the successor. And then well, oh yeah, by inductive hypothesis, we can bring that n into the power. Yeah, so we're here. And then a times m. I kind of need to just draw this, I feel. I'm so rusty, y'all. I'm so rusty here. What is going on here? I want to get this. M n plus m. Do we have that? Yeah, we do have that. We do have this. Okay, yeah. We do have this rule already. So the challenge is like which theorems, which facts about powers do we have and which ones do we not have? We do have this. Right? This isn't a definition, but it's like because a to the b times a to the c equals, let's use x, y, and z because those are unbound variables, x to the y plus x to the z equals x to the yz, oh wait, y plus z is what I meant. Yeah, x to the y plus x to the z equals x to the y plus z, right? Then we can add these two exponents together. And then that equals m times n plus 1. And we would have to say by left distributivity or something. But there's like, we have a proof that that next equality. So I'll make this really explicit. By left distributivity of multiplication, we have this next little inequality, or not inequality, equality. And so we are done. And then you draw a nice little square. And the cute little square is like your signature that says, we're done, voila. So because this is the right-hand side that we wanted to show, all the way back here. So we started from this left-hand side, and then we wanted to get to this right-hand side. And that's exactly what we got to. Right? Yep. I just took out the multiplication, but yeah. Let's take out some unnecessary multiplication symbols where I feel that they're not necessary and that they obscure the readability. Readability is very important, everybody. In code, in math, style. It's basically style. Don't write overly rigid style guides. So here's our classical proof that we want. Now I'm going to translate this to a lean proof. So first, induction on n with, I'm going to reuse the variable name like I did in the proof, but other people would replace that with h or something else. I don't like doing that. Induction on n, reusing that variable name, and the inductive hypothesis. Okay, so we're going to do an induction proof. That means that here we have a new goal. I don't know. First we show the base case, which is basically this stuff. So in lean, the state machine has changed to, we have a goal that we want to show this, right? So we rewrite the left-hand side with, we can rewrite the left-hand side with the rule pow 0. After doing this, so let's add in like little, maybe I'll distinguish lean statements this way as opposed to English sentences the other way. I don't know. So now our goal is currently this. That's kind of cursed, isn't it? A little bit, is it? After rewriting pow 0, our goal has transformed to anything raised to the 0 is 1. And 1 equals a raised to the m times 0. Right? Now we can rewrite the right-hand side with multiplication by 0, right? And our goal has now transformed to anything multiplied by 0 is 0. So we rewrote that little term. And now we can rewrite with PAL 0, and our goal transforms to anything raised to the 0 is 1 for any natural number as the base. And now we say REFL, which means the left-hand side equals the right-hand side. Like in proofs, you often say that, thus LHS equals RHS, and we're done. Therefore, that's what RFL means. It means reflexivity or reflection, reflexivity, something of that form. Now, here was our human proof. Why don't we keep the entire human proof here? And now we're showing the lean state transitions here in these multi-line comments. Really, I should do the opposite, but I'm getting annoyed. I don't want to rewrite everything. Next, we prove the inductive step. Where is it? We want to show this. So, in lean, now the state machine has goal is this. And we have the hypothesis that, where is it? I wrote it here. Let's keep it. Our hypothesis is defined like this. A to the m raised to the n equals a raised to the mn. And our goal is this. So we do the same we do the exact same steps that I did in the human proof. Let's rewrite the left-hand side with the definition of power raised to a successor. Oh, in lean, we're not using plus ones everywhere. In lean, or technically in piano arithmetic, we don't use plus ones, we use successors. So the successor of n is the same thing as n plus 1. And I don't think I had any plus ones in the base case. All right. So are we still compiling? Okay. So after rewriting power successor, let's start building our correct style. Okay, so correct style can I uncomment with like, yeah, okay, so command slash will uncomment like a lot of text editors will, like a lot of code editors will. And I want to come back to our half and half. Okay, maybe we'll just upload this as a single video. So we assume the inductive hypothesis. I'm just going to do it. I mean, that makes it feel like it's not a variable, like a mathematical variable, but a hypothesis. Let's get some decent names for things, I feel. So that's what I feel. I feel like that's a better name. But what do I know? I'm not a lean person. So right now we have a hypothesis and a goal. And we can rewrite the goal with our theorem our definition of power raised to the successor which transforms our goal as a to the m raised to the n times a to the m. And now the right-hand side still is written this way. I want to take advantage of working from the left-hand side and the right-hand side to clean up this proof a little bit, because there's that step that I got stuck on somewhat before. So I'm going to rewrite the right-hand side of this line as with multiplication by a successor. That's what I would expect it to be called. I don't have these memorized. I just think that that's what it's going to be called. So we're replacing m times suc n with mn plus m. Yeah, that's what I would expect. And now, did that work? Are we currently here? Nope. A raised to the m raised to the n on the left-hand side. Okay. A few things went wrong, didn't they? Where did we get to? A raised to the m raised to the n times... What the heck? Okay. We didn't get as far as I thought. What? Goal? Why would that be the goal? Or we didn't even compile this first line. Induction on n with n and hypothesis. Okay. Let's comment everything. This is a classic trick in software engineering. You just comment everything, get back to a good state, and try to compile the thing again. Because you can't tell if the compiler is broken or like what's going on. Where are we? A raised to the m raised to the n equals a raised to m times n. I think that if we claim induction on n this way, what if we go to typewriter mode? Crashed. Go to editor mode and fix your proof. What went wrong? Error updating, error fetching goals, client is not running. Try again, please try again. Click. No responsivity yet. Okay. Something went wrong here. Induction on n with n and hypothesis. What happens if we comment this line as well? What happens if I refresh the browser? What happens if I uncomment our first line? Okay. All right, so we did get to the next step. I think that the system just crashed and it never ran in the first place. So let's uncomment lines one at a time. Or actually, let's just see if we can we uncomment the entire base case? Did I get that correct? Yeah, all right, so we updated to the inductive step. So we have the inductive, we assume the inductive hypothesis here, and our goal is now to complete the inductive step, which is like showing that every domino is close to the next domino. While we're at it, let's just change some style. Because I learned that I can command / to uncomment a large section. I wish that the editor wouldn't complete the second if one had already been written, but no biggie. Anyways. Okay. So this is how I like to do it, so that I can see what the state is of the machine even when I'm in editor mode. So now if I grab all this and command slash, yeah, okay, it did the right thing. It removed one level of comments. Cool. Overall, I mean, I know that I'm like kind of being snarky sometimes, but I really, really love this entire environment. It's really super impressive to me, like how powerful and usable it all is. Okay, so did we get a raised to the m raised to the n times a to the m equals a raised to the mn plus m? Cool, we got there. Yeah, all right, so we're still working. We're still working the way I wanted. And now I want to get the left-hand side and the right-hand side statements to meet in the middle, right? So on the left-hand side, a raised to the m raised to the n times a to the m. Oh, yeah, we can apply the inductive hypothesis. How do I type this again? Apply the inductive hypothesis? Is it apply? Is that right? Apply hype. A raised to m raised to n. Do I put this in a list? How do I apply the inductive hypothesis again? Because we assume this part. We rewrite with that, don't we? Yeah, that's what it worked. Okay, so we have this assumption. So this is part of our truths. And so, yeah, no, this makes sense. So this is like a rewriting rule that we have in our toolbox temporarily as an assumption. And so since it's a rewriting rule, it says that anytime that you have these symbols together, you can rewrite it as these symbols instead. Okay, so now let's see if I can do this in my head instead of peeking. So now the goal after applying the inductive hypothesis should be a raised to the, I'm going to use shorthand even though, goal raised to the mn times a to the m equals a raised to mn plus m, right? And now we can rewrite using, I think, multiplying powers. Or is it pal multiplication? Or is it pow add? Pow. This doesn't seem to work. Okay, so multiply power. So first do a multiply and then raise to a power is what this theorem has. So what we want is we have two powers and then we multiply them. Let's try it. Pow mul. I don't think that that's correct. Pow mul. How do I read this thing? Pow mul Yeah, is a power raised to a multiplication. So I want this in reverse, don't I? I want... Okay, I can cheat because I think I know what I'll type to get to rewrite the right-hand side, but I wanted to rewrite the left-hand side. Yeah, let's first do it with the right-hand side so I can get this working. Pow add, right? And now, after rewriting that way, the goal should be a to the mn times a to the m equals a to the mn times a to the m. Is that what we got? A to the mn times a to the m equals a to the mn times a to the m. Cool. And left-hand side equals right-hand side, so we say that this is reflective and therefore level complete. Great. Now, if I did the left bracket here, then we are rewriting the left-hand side, right? Yeah. Okay, so that's the one I wanted. Like, I wanted, to bring this m into this exponent on line 46. Yeah. Okay. Or, whatever. Yeah, same. I wanted a raised to mn time plus m. So, it's things like this that make lean a little fiddly to me. It's just like, do I use the left arrow or not? Like, what's the name of the right theorem to use? Because usually in a math proof, you would say whether you're rewriting from the left of an identity or rewriting from the right of an identity, you would still just say by distributivity of multiplication. You wouldn't say by distributivity of multiplication in the forward direction or from the reverse direction. So it's taking me some time to get used to that style of proof writing. Cool. I think maybe we'll just leave it like this, just a video solving one theorem. Can we do one proof and show one proof to the world of what proving a theorem looks like in classical math writing, as well as in lean? So, let me pause. Hey, Jeffrey. Hey, Yuvraj. How's it going, y'all? Good to see you both. Hi there, what's up? Are we doing exponents? We are doing exponents, dude. I'm sorry if I missed you. I don't know how long ago you commented that because I was so in the zone. What we're doing is we are proving the power rule of exponents, that if you raise an exponent to another exponent, that it equals raising to the multiplication of those exponents, to the product of those exponents. So successive powers equals a product of powers. That sounds snappier. You want to get mathematical statements to have a ring to it so that you can say successive powers equals the multiplication of powers or something. Or the product of powers. Product of powers has a nice alliteration to it. And so even though all those different English sentences say and mean the same thing, there's something memorable about some ways of saying mathematical statements. And I don't have other good examples right now. I don't know, the infinitude of primes or something. Like you have like nice little catchy sayings that sound nice and aesthetically sound very nice. And they have a ring to it and they roll off the tongue better than saying the fact that there are infinitely many primes. And so far, if I have a criticism of Lean, it's that I feel like writing proofs in this style, rewrite pow add, left arrow pow add, rewrite bracket mole suck, it loses some of those aesthetics of English proofwriting, and it loses some of the aesthetics of memorable, catchy phrases. Like you can still have that in comments and in the paper proofwriting, I suppose, but it loses some. It certainly loses some readability. And I think style and readability is not trivial. I've worked at some companies where people consider like we have a style guide and we've chosen one style and it's completely arbitrary and it's completely trivial and it's not worth talking about style. It is worth talking about style, y'all. Like style and aesthetics help you learn things. Allowing for different styles in a code base allows for people who think differently to internalize that knowledge, like whether it's like a piece of code or something else. And it can be quite, I don't know, it can be quite a friction point if the line breaks don't match what your mental model has. And in reverse, if you're reading somebody else's code and the indentation is completely inconsistent, that can break your mental model too. So like there are times that style guides and linters are so like just necessary, but then there are other times when they can go too far, I think. And this is pretty different because it's not quite style like how we would write something. Like there is one way to write the rewrite tactic as far as I know in Lean, but I'm talking about the aesthetics of readability. Readability to me really, really matters a lot in classical mathematical proofwriting, like to write out full English sentences or something that reads like an English sentence, even if there are a few symbols. Like use the symbols sparingly. My professors in college would dock points and actually subtract points and say, do not use the upside down A. Just don't do it. It's a bad idea. Like it is fancy, but it just looks like hieroglyphics. It's not worth using upside down A, in my opinion, versus for all X element symbol Z. You know, like I don't mind all the symbols. Like it's a taste thing, and it's hard to like. I really think aesthetics is just hard to draw a clear line in the sand on. You can't really. I don't know. I don't think that you can teach RuboCop how to style guide a mathematical proof. You know what I mean? Like, you can't get a linter to capture aesthetics in mathematical proofwriting, in my opinion. All right, so we're going on a tangent here. I think that, I don't know. I'm getting used to it, but I'm just old school, I guess. Like I like the little paragraph, even if there is shorthand like WTS to be want to show. Yeah. But what we lose potentially in like aesthetics and readability, we gain an infinite amount of value by the fact that the computer can actually run this proof and tell you that it's correct. We don't have that right now in white papers. It's, from my experience, being able to run a program that tells you if your primary program or your primary work, being mathematics, if your primary logic and work is correct or not. Writing a secondary program to do that is so unbelievably valuable, and it's worth it, even if it is annoying and it slows you down and it's like eating your vegetables or something. To me, we should continue writing the English white papers in paragraph form, and we should write it again in formal mathematics, in lean. And it's just like test-driven development, in my opinion. Whether you test drive, meaning you write your test before your code, or if you test after and you go back and actually write your unit tests and your integration end-to-end tests, etc., after shipping a feature or whatever, it's worth it. I think that there's a lot of parallels from the software industry that a pure mathematician is never going to learn about unit testing, I don't think. But that type of skill is becoming super valuable, I think. So I can't wait. I want to get involved. I want to become an open source contributor to this whole project because I think it's so dang cool. All right. Thank you for watching. I hope you have a wonderful day. I'm going to get some lunch. All right. Bye. Oh, also, I'm available as a private tutor. If anybody wants a private tutor, shoot me an email at themathhobbyist@gmail.com. I can teach, I feel, pretty much any high school, elementary school, or undergraduate math, like blanket statement. I charge on a sliding scale all the way from free to expensive. So hit me up, and I think that we can work something out if you're curious. Shoot me an email, and I hope to hear from you. All right. Thanks, everybody. Also, I'm available as a guitar teacher or a coding teacher, private tutor in iOS development, Vim, and classical guitar. I'm quite good at those, and test-driven development. All right. Thanks for watching. Bye. Bye, everyone.